Hello, welcome back. In the previous segment, we discussed the fact that the address of BSS segment is the same between runs. We can take advantage of that to perform exploits. Let us take this example, right? You have a global variable, global buffer, 80 characters are allowed, right? That's the declaration here for the global buffer. And you have your main function, which takes argv1 as the input. I have not checked whether argv1 actually exists, but I assume argv1 exists. Otherwise, you get a null pointer dereference there, which has to be fixed by checking whether arg count is at least 1, right? In fact, arg count has to be at least 2. The first argument is the name of the file. Argv1 is the argument that the user is going to send in. So that data will be copied to the local buffer, which is declared here. Of course, there is clearly a buffer overflow. If you feed in 80 characters or more from outside, you will already overwrite some stack content. Okay. In this case, right, we're also doing one more thing. We're transferring the local buffer to global buffer. Okay. So now the question is, how can we take advantage of the BSS address not changing between runs to perform an attack? So the idea is that we don't have to look for the address of the buffer, right? The address of this global buffer is clearly part of the assembly. Let me show you why I say that. If you look into the disassembly of this code and disassemble the main and look at string copy, the second string copy, the first argument is a number 804A040. That actually is nothing but what? Is the address of the global buffer, right? If you go back to your code, you see that the global buffer is the first argument. Okay. We can grab the address directly from the assembly code because this is part of the BSS segment. Okay. That means if anyone has access to the binary, they would know the address of this global buffer. Then they can perform an exploit just making assumption about the address. Even if ASLR is turned on or off, it doesn't really matter. As long as the BSS segment address is not changing, right, which is the case in the default compilation of the program, you can take advantage of this fact. All right. So what will be the attack in this case, right? I've already compiled this code and analyzed the assembly for you, so we can quickly draw the stack layout, right, and talk about the attack. Okay, so you would have to fill up 80 bytes, first of all, 80 bytes of buffer, right, to fill up the buffer. So 80 bytes. And then you need to fill up the EBB. I have already analyzed the assembly, and therefore I can draw this stack layout informally. This is the EBB of the caller, right? And this is where the EBB is going to point to. Okay. And then your return address, right? This is basically after main is done with the job, it should return to libc, right? That's the return address. Okay. So in order to perform this attack, right, we replace the address of the return address by the global buffer. Okay. So the idea is that global buffer is somewhere we don't know exactly. It's not part of the stack. It's here, global buffer, right? What are we going to do? We're going to replace the return address, right, by the address of the global buffer. Okay. So the return address is going to point to the global buffer address. All right. That's interesting. What is the shell code, or where can we put our shell code? I mean, the attack surface is through argv1, right? Argv1 is the input we can control. So we need to fill up some data, enough number of data, like enough 80 bytes, whatever, right? And copy that. Eventually, that will be copied to the global buffer. So the global buffer will also have exactly whatever you see here. All these 80 bytes, right, will come here also. So you will be putting your shell code here. Okay, let's say the shell code takes 24 bytes, then you will be having 24 bytes of shell code here. The same 24 bytes will be sitting here in the global buffer. Okay, because you're making a copy of local buffer into global buffer. So of course, to perform the buffer overflow, we need to fill up 80 bytes. If the shell code is only 24 bytes, you fill up the remaining bytes with knobs, right? And then you do the same with EBB also, and then replace the return address by the address of the global buffer. Okay. When ret statement runs, right, when this return statement runs, what is the meaning of red? Red means pop to EAP. So EAP now will point to the global buffer, okay, which has the shell code, and then the code will run. Okay, that's essentially the idea of return to BSS, which is a technique to overcome ASLR when you can use the BSS segment address, for example, in this case, the global buffer. Okay. So the attack is basically taking advantage of the fact that some addresses don't change between runs. And if the attacker can get access to the binary, they can extract the address of the global buffer, and then they can perform this attack. Of course, there are a few things you need to notice here. The stack protector is disabled in this particular binary just for education purpose. You should not be disabling the stack protector. And I have made the stack to be executable also, which is not the thing that you would need to do in general. But for this attack to work, I have disabled some of the controls to demonstrate the idea of return to BSS. Okay, so this attack is actually called return to BSS. Yeah, ret to BSS, which makes sense because we are returning to an address which doesn't change. That is, the BSS is basically block symbol address, right? Which is not changing between runs. Block symbol segment is the meaning of BSS. Okay. All right, let's go ahead and generate the payload, and then we will look at the content of RV1, whatever we are going to pass from the command line. I have written this payload generator, right? Payload BSS dot exploit BSS dot Perl. As you can see, my shell code is here. This is my shell code, which is essentially copied from the shellcode database, and it has only 24 bytes. And then I replace the return address by the address of the global buffer, which is exactly the number I showed you inside GDB. This is getting directly from the binary or assembly code, and you write it in the reverse order because of Little Indian, and then fill up enough number of knobs. Okay, so why do we need 60 knobs? Because 60 knobs plus 24 will be 84. 84 is exactly what we need to fill up to reach the return address. Remember, 80 bytes of buffer, 4 bytes of EBB means 84 bytes. That is why I'm filling in 60 bytes of knobs. And then the return address, right? I'm replacing the return address by the address of the global buffer. That's the reason why my payload will have shellcode, followed by padding, followed by return address. Okay, and then I open a file called payload underscore BSS for the write mode. That's why you see a greater than symbol here. This is the file handler. And I write the data that is generated by this line of code here, and then I close the file. Okay, so let's go ahead and run this thing, right? Perl exploit BSS.perl, which will create a file called victim BSS. Okay, this is the file. We can even do hex dump and see the data inside, right? And you can see that it's not victim BSS, it's the payload BSS. Yeah, this is better. So the payload BSS is what the victim Perl, the payload BSS is the file generated by the exploit Perl script. And you can see here, everything from 31C0 all the way to CD80 is our 24 bytes of shellcode, and then 60 bytes of knob, and then your return address, which is the address of the global buffer. Okay, so this is the payload. We are going to feed it to the binary. So the binary is called victim BSS, which takes one argument. So I'm going to pass the payload file. Now you should watch that I'm going to get a new prompt. Currently the prompt is Dharma : program. And if you run this one, you get a new prompt, yeah? Because I got a new shell and I can exit here. I go back to my previous cell. So what did we learn here? We learned that we can take advantage of the fact that BSS address segments. What we learned is that we can take advantage of the BSS segment, which is not changing the address between runs. We can use the binary to reverse the address of BSS segments. And if we can somehow fill up the shellcode inside those buffers that are not changing the address between runs, we can hard code that address as part of the exploit generation. That's what we did in our Perl script. Okay, that's all. Thank you very much for your attention.